Okay, yeah. Good afternoon. Let me open a mouse or a laser here quickly. Okay, yeah, so I changed my title, but it's the same thing. I said integrated packaging strategies to address the modern challenges. So yeah, just to kind of approach these things that we're now facing. So we're very reliant, of course, on container shipping for all our exports, especially with South Africa being very isolated in these markets. This is an old estimate, but it's about 45,000 containers shipping permanent stone a year. I kind of bumped it up because it was a 2019 figure. But the expectation is just that the demand will increase. People want year-round fruit. So we're going to become more reliant on this system. And then, of course, lately, the big challenge is just fuel costs. And the shipping lines a little bit taking, well, not a little bit, taking big advantage of the industries at the moment. So they're reporting record sales or record profits. But yeah, it seems like it's landing on us for costs. And it seems like that trend is really going to increase. And then on the other side is just a high demand for a greener product. So for us to ship fruit that are greener, with a cleaner sort of carbon footprint kind of story, they want to hear that we're doing something. So yes, the current sort of packaging sort of approaches that are in use, when we load a container, we see sort of about 10% of the floor area just not used, and it's kind of a given that it will be like that. And if you look at that container as well, only about 64 to 67% of that container is actually full of fruit. The rest is either air or it's just packaging material. So yeah, if we could use that floor area, so just the 10%, that would of course mean about 4,500 containers less, which is a marked improvement. That's about $30 million. And then of course, yeah, just a big savings that we really need at the moment. Yeah, I think one of the things to note is that there's no universal ISO standardization for packaging. But if you look at the pictures on the right-hand side, this is actually for citrus. Everybody's kind of doing the same thing. So this is now a depot in the Netherlands, in Rotterdam. And the same is for melons and, for all of them. It's all the same carton footprints and mostly the same pallet footprints, although there are often sort of smaller ones and funny shapes. Generally, everybody's copying each other. But yeah, I think at the moment, the world is kind of reevaluating how we use oil, how we use plastics, how we're even communicating at the moment. And I think it's maybe a good time to just look at how we are shipping our fruit as well. So yeah, the problem is how do you now optimize a package design or packaging system for your container, and of course for all the facilities that are linked into the system. And the answer is it's very tricky. Actually, they call this an NP hard problem. That's a non-deterministic polynomial time problem. So the problem is when you have lots of sort of dimensions in the problem, and if you change one of the dimensions, so like the footprint of the carton, for instance, it doesn't linearly sort of correlate to other changes. So you have to rerun all the other combinations to identify what its impact will be on cost, let's say, or one of the other parameters that you're evaluating for. So it's kind of impossible to know if we have the best design now, or if you do develop something else, if that was actually the best design. But yes, this can still be simplified. So I've kind of given a little bit of example. I showed sort of a graph here. So this is your optimal design rating, whatever whatever parameter you're using to I don't know, test this carton if you have something new. Probably that would be cost, that right at the end of the chain. What was the cost to you? Did it save you money or not? And I think at the moment, this is of course your design space, all these different options that you have. I think at the moment we're kind of sort of at this local optimum. So if you now change a design, it will get worse. And then somewhere along this plane, there is probably a global maximum, like the best thing you could get. And the trick is to get us from here, and not be discouraged if we find something sort of in the lower point, and then reach this maximum. Okay, so yeah, of course this graph is now like a two-dimensional or even one-dimensional problem, and here's sort of an example of this space in a two-dimensional problem. But the reality is we're probably looking at maybe 100 dimensions or more. So it really is it's a difficult sort of problem, but we can simplify. The one thing we know is that the container is immutable, so we cannot change the internal dimensions of the container. It's of course being used by many other industries across the globe, and we're really not that important in the shipping line's eyes. They have bigger players that they would like to accommodate. So we can say that that's immutable. The pallet footprint, that also has some nice restrictions. Many of these facilities have sort of these sliding racking systems, so the pallet base would need to fit on this thing. So effectively it can be the same size or it can be smaller. And then of course we want to optimize with respect to cooling performance. We've just heard a lot of talk on why cooling is important and how the conditions are important. And then of course we also want to optimize the packing density in the container. Okay, yeah, so I was given that task. I think this was sort of part of my PhD. And I was unfortunately asked to think outside the box, so to speak. So we kind of went two routes. We went with this test carton, and then we went with this hex carton. And basically the idea of the hex was that it's hexagonal. It's kind of impossible to make a hexagonal box, but if you sort of mate these two cartons together, it's a hexagon carton or hexagon shape. And then the other one was the test. So this carton is kind of special because each face on each side is totally sort of unique. And you would need some sort of printing pattern to kind of stack it correctly, and then everything is in alignment. So you get very good cooling when you use it. Well, I just wanted to show you kind of a container in this picture. So in these following pictures, this is from the top. So this is now if you put your little pallets, those pallets that I just described, on the floor. The first three are your standard kind of Mark IV carton. This one is 20 pallets, these are 21 pallets. I think there's now a 22 pallet solution with some trickery, but this is what I had at the day. And then the test is sort of over here. So if you're using now, let's just work with 21 pallets, then you're using 92% of your floor. If you're using this new test design, you would be using about 99% of your floor area, and then with the hexagon sort of design, you'd be using about 97% of your floor. But of course, those aren't good metrics to kind of analyze, so we'll just go a little bit deeper. In this graph, the blue is kind of showing how much fruit you actually have in the system or in the container. The yellow bar or section of this bar is the packaging material, and of course, you know, that's a tricky one, and it's actually something you would need to include in the optimization problem, because maybe in this hex example, for instance, we have less packaging material, but maybe it would then need to be stronger, which might make it more expensive, and yeah, it could become tricky. But the point here is that there's less packaging material, and you could accommodate that in various ways. But yes, if you use now the hex, well, let's go back to sort of standard. If you had 21 pallets, Mark IV, you would have now about 19.8 tons of fruit in the container. With the test, you would have about 19.8 as well, but potentially sort of more, well, we'll get into cooling just now, but there's some other benefits. And with the hex, you have 22.4 tons. The next step in sort of looking at this cartons, we looked at sort of cooling, and we broke the problem down. First, we looked at horizontal, so that's pre-cooling scenarios, and we used this sort of in a simulations system. So this is just evaluating heat transfer and airflow through these cartons, and then also vertically, just one row. So just looking at how the packaging resists airflow, etc. Also for airflow and cooling. Yeah, I think the interesting part, we took these parameters that we got from these simulations, and then we put it into a much larger simulations. So we just defined them as a porous media, and then we simulated an entire carton. I now regret that I didn't show you a full picture of this simulation, but it's okay. You can see it on Friday. So for the evaluations, here's the sort of three containers using Mark IV cartons, and it's pretty standard. This is for airflow, and this would be the refrigeration side on the left. Yeah, and it's what we expect. Very high airflow rates on the refrigeration unit side, and then very poor cooling and flow rates on the right-hand side. So basically everything is bypassing you on this side. But when we use the TESS and the hex packaging systems, because we're covering the floor area, because we're using all the spaces, our airflow uniformity is excellent, and they would carry over to cooling. So therefore your control over the environment of these fruit is actually far superior. Okay, and then this is kind of just reiterating what I said with some vector plots. Maybe we'll get the slides to have a closer look. Okay, so to conclude a little bit, maybe a bit slowly, So, as I said, packaging designs are really optimal at the moment. We're really at a local optimum point, which is becoming less acceptable as time goes on. But yeah, I think there's a lot of pressure. I hope everybody agrees with me. It'd be interesting maybe at question time to hear. But the pressure is to do something different and to do something more optimal. I think one of the big problems, and I just said here, is for one player to now actually try and make a move on a new design, because it's very risky. You could end up with something less optimal and really expensive. But yeah, somebody will have to kind of do it. I think probably the only way it would be achievable is to get sort of a multidisciplinary team and approach the problem together. And then, yeah, like I said, also, it can be simplified, this problem, with an approach of an immutable container, locking yourself into the boundary conditions of the pallet base, and then just optimizing for the criteria that you would need. And then what I kind of said here is just, I mean, I looked at packing density and cooling, but really you would need to look at other things. For example, manufacturing cost. Can your carton assembly machine assemble these cartons? Are the fruit being protected properly? How is the acceptance on the market side working? Is it compatible with all the facilities that it's working within? The supply chain integration, can it go on a truck, can it go on the forklift, etc. And then of course all of this would have to be holistically combined into some sort of cost-benefit analysis. And yes, I think that's it. Thank you very much for listening.